The second mode of calculations is when they refer you and ask you to use average or mean bond enthalpies values. Now, in that case, the reactants and products, they all have to be in gaseous state. The other thing you have to remember is two facts: that bond breaking, which takes place on the reactant side, is endo, and it has a positive value. And on the other hand, on the product side, you're forming bonds, it should be exo and negative value. The last thing to do is you sum them up. So delta H of reaction is sum of bond broken reactant minus sum of bonds formed. Now this minus comes due to the fact that it's exo. The one other thing you will be challenged is the word average or mean. Why is it in front of this? You have to realize that this information that is gathered here, they come from compounds with similar attachments. For example, if I go after methane, CH4, and if you compare it to another compound such as methanol, they both have a CH attachment. And when I break this bond compared to this bond, in reality, there is a difference. But we are going to average them up once we measure them exactly and give you an average value. So the average is not reality, and that's why when you calculate delta H of reaction using average bond enthalpies, you are always inaccurate. You are way off from reality or theoretical values. Now let's apply it to an equation. I went after Haber process. The first thing to do, realize they are all gases, so I can use average bond enthalpies. Balance the equation, so I put a 2 ammonia and 3 hydrogen. Then you have to remember some Lewis dot structure, because nitrogen to nitrogen is either triple bond, strongest, or double bond, or single bond. In this case, when you do Lewis dot structure, you see it's triple bond. Hydrogen is easy, single bond. And ammonia, hopefully, is easy for you. It's a pyramid with single attachments, 2 hydrogens. Now we are ready to use the values. This is what I'm breaking, so I'm going to put it in one category. I'm breaking 1 triple bond to nitrogen, 3 single covalent bonds between hydrogens. On the product side, I'm breaking, this is also important, some students make a mistake, 1, 2, 3 attachments nitrogen to hydrogen, but don't forget your coefficient of 2. Therefore, I'm breaking 6 nitrogen to hydrogen attachment. I'm ready to put numbers down. Nitrogen, triple bond nitrogen is 944 kilojoules per mole, plus 3. Hydrogen to hydrogen is 436, each one of them, minus 6 nitrogen to hydrogen attachment, and that value is, if I find it, right here, 388. When you do this algebra, you get delta H of this reaction equal to negative 76 kilojoule per mole based on this data. Now what I want you to realize, the theoretical value delta H for this reaction theoretically is negative 92 kilojoules per mole. So you are few kilojoules away from their reality. And why is this not accurate, not exact? Because I'm using average or mean bond enthalpies. That's why I'm not accurate.